because the pump is providing the pressure, right? So you can neglect the pressure losses on that thing. Okay, so when you open it, you will get the free delivery. So actually they start from here.
Start what? Start
From the free delivery, which means this one is totally low, right? Whatever you have. So initially, this one and that one will be the same, which means the head is 0, right? Then they will close the valve. When they close the valve, of course you will see that something moving up, right? It's coming, moving up, moving up, moving up until you fully close the valve. That's why it's called shut off, which means you close. Right? So when you fully close, then you will get the maximum pressure you can get from that pump. You know how it goes, right? From the, if you have a conservation of energy, it will be P times volume, right? This is the watt, times the mgh, right? Sorry, not time, plus the half mv squared. You know this? In this case, you have joule. Okay. Right? When you divide this with the mass, or you divide it with the volume, you get pressure. Right? Here become rho gh, and this one become rho p squared. All of this you get Pascal. Okay. Then you divide this with gamma or with rho g. When you divide this with rho g, you get P over gamma plus h plus half p squared over g. So if you look at it, the unit will be. So from here to there is time gamma. From here to there is. So this is how it works. It's very simple. I do not know whether in your previous lecture when you use this. Head, pressure, energy. Very simple, right? So if you get the head, you can calculate the pressure. If you know the gamma. When you know the pressure, you can calculate the energy. When you know the volume. As simple as that. Okay, so that's what you get. So if you get the head, you can calculate the. Where is it? Yeah. If you get the head, you can calculate the power needed. Yeah, because you get the energy here. Joule. Joule divided by second, you got the watt. Because instead of mass, over there you get mass, flow rate. Right? This one is kilogram per second times meter per second square times meter. Right? So you get kilogram meter square second square, or kilogram meter per second square meter, which means Newton meter, which means joule. So okay, so you know that pump will always behave like this. Either it has a high pressure or it has high flow rate. You cannot have both. So yeah, just like choosing your loved one later on, right? Whether you got them a very smart but arrogant, or not so smart but very obedient. Right? You have to get your optimum condition, right? The optimum one. Okay, it's rarely you get the princess who is very rich, handsome, obedient, love you. Who are you? So usually you will be in the middle here, right? Maybe you will get a rich couple, but a bit stubborn, right? Or maybe you get a not so rich couple, but having a good time. Okay, so that's about what's like. Okay, the same goes for the pump. Either you get a very high pressure or very high flow rate. Okay? This is a normal pump. Some pump has a very complicated story, like this thing. This pump, if you see the characteristic curve, it has some, this valley, right?
So it goes down, reach some level, and it goes up again, and then it goes down. So in this case, if you put your operating curve, or the system curve, you will find a 3 point instead of 1 point like this. In this case, you have only one operating point, right? This operating point is the where you need to set your pump to work with. So if you know your Q, if you go to this side, you get your H. Then you can calculate. You get Q, you get H. You can calculate the watt needed to drive the pump. Okay. So this is what I told you, the pump family. Okay, why we have a pump family? Because when the manufacturer create one pump, they do not want to just use it for one size. You know, because let's say some of you want, oh, I don't need the big pump, I want this small pump. Okay, you get that pump. Then someone else say, can you give me a bigger pump? They cannot say just, okay, wait, I will design for you. They will not do that. So they have a family of pump. Not only this one, they have maybe a lot. Okay, so you can see here, this one is the smallest version, bigger, and the biggest. And if you see at it, the bigger the pump, the better the efficiency. Right? If you look at it, see, the efficiency is the green color, it goes like this. Topography map. Right? I would love to put this one in your variable. Right? And you can draw the system curve here, find the best pump and so on. Yeah? It happened last time. May happen again. Okay, so that's what you have. And this is the power. This is the peak power. This is the maximum power will be drained by the pump. So you can see here, 15 horsepower, 7.55. Right? And if you realize, because our pump manufacturer usually come from US, you see all the unit. All the unit, like it or not, you see it in British system. Okay? This is British system, but not used in British anymore. It is used in US. Can you imagine? Okay, one other important thing is, you see up there, you get the required NPSH. This is net pressure suction head. This is the head required such that the pump will not experience the so-called cavitation. You remember? If you are having a low pressure, water can boil at low temperature, right? We call it a cavitation. Cavitation is not good for a pump because it will create the so-called hammering effect. It will explode, and it will chip the blade. Okay, one pop, 2 pop, it's okay. It's just popping, right? So it's just okay. But you have 1,000 or even million of it, for a long time, you know it's getting worse, right? Like a torture. Okay? So, how do you get the system curve is we will use the so-called Bernoulli equation, extended Bernoulli equation, where this one is obtained from the manufacturer. Okay? Just to give you an idea how we can do it, okay? Look at that system, very simple system. Right? Of course, your exam will not be as simple as this. A very simple system, you have a pump to drive the water from a low reservoir into the big reservoir there, over there. Right? So just moving the water from low reservoir into the elevated reservoir. The pump diameter is 15 cm. The total length between the pump entrance and exit is 16 meters. Okay. Minor losses are given, right? And then the friction factor, okay. This one
depending upon your examiner, if your examiner want to give you a bit more challenge, the F will not be there. If it is not there, don't blame your lecture. You have to find it. Right. It is not that, oh, the lecturer is forget, so we will get a free bonus mark. No. No, not saying that lecturer never forget. I forget a lot of things. But if you got this, you got F, your lecturer is just want to challenge you. Okay, so if you do not get the F, don't ask. Just do it. Okay? Just do it. Okay? But in this case, it is given. So you need to determine the capacity or the Q or the operating capacity or what is the rate of the water flow between two tanks. How do you do that? The pump characteristic curve is given here. This is the efficiency. So this is the best efficiency point. And this is your characteristic curve. How do you do it? Yeah, of course, with the formula given in the appendix. Very easy, right? Which formula is your problem? My problem is to dump the formula. Just find what is the Q. You are given these two conditions with this explanation. You need to find the Q. How can you do that?
Find out the intersection.
Yeah, find the intersection between intersection between.
The two times. Efficiency and.
I'm not saying about efficiency. Yeah. The operating point is the intersection between
The pump performance.
system curve and pump curve. How do you get the system curve? Yeah? Or the extended equation. Okay, then do it.